Welcome back again. So we continue our work on dynamic optimization in continuous time. So let's look at another exemplary problem. Okay. Let's suppose we have this consumer. Okay. So this is a typical problem of optimal growth. We can think of this as an entire national economy, by the way. Okay. So this part is the same. So there's this utility function. Now what we want to do is to maximize this entire thing under these constraints. Okay. Now what you see here is a simple optimal growth problem or capital accumulation problem. Okay, so you have capital stock. Kte is your capital stock. Ct is your consumption. Now, obviously, you can produce stuff with a production function. So U is a utility function. Okay, and F is a production function. Okay, so you can produce some stuff using your existing capital stock, and then you can consume some of this production, and whatever you do not consume becomes your saving. All right. So here in this problem, the cake could be reproduced, right? The cake could be reproduced. It is not fixed. So this one will be called your state variable, and this will be your control variable. Okay. Now this is just another simple example. You may also imagine this. You may imagine a person still obtaining utility from consumption and still discounting the future at a discount rate of rho, okay, and maximizing this with this control variable. Now you may imagine that this is actually wealth. Okay, so consumption will be non-negative and there will be wealth accumulation process. Okay, now there will be some return on wealth, and that return will be, of course, usable as consumption, and then you have the initial wealth stock. Okay, so another problem would be a firm problem. Let me use this space for that. So suppose that the firm wants to maximize the value, the market value of it. So here we have, again, an infinite horizon. Now there is a profit stream. This profit is discounted at this market interest rate, R, okay, where R is positive. Now profit will be defined, so this is subject to. Now profit will be defined in this way. Let's say you have a product you sell, okay, the product you sell is produced using capital stock, okay, then you have this investment expenditure, okay, and obviously in such a problem IT is your state variable, sorry, control variable, how much to invest, right? This is your control variable. Now, for this problem, suppose that there is a compact set I min, I max, okay? I can explain why I'm using that particular assumption. But suppose that there is this maximum amount you can invest and there is this minimum amount. Then your accumulation equation, of course, becomes what? Right? So there's this delta, which is the depreciation rate, right? So you invest this investment, if it is larger than the total depreciation, it increases your capital stock increases your production increases your profit. So here, think about the trade-off, all right? So if this is an economic problem, right, there must be a trade-off. So where is this trade-off? Once again, we have, of course, this as well, okay? So where is this trade-off? If I do not invest much today, if I keep my investment low, what do I have? I have a larger profit today, right? I have a larger profit today. But if I increase my investment, I have a lower profit today, but larger production tomorrow. All right? Again, I am allocating resources in a dynamic manner. All right? Same is here. If I consume more today, I obtain more utility today. But I have less savings to become part of my wealth stock tomorrow. Okay? These are the simple trade-offs that we observe in such optimal control problems. All right? So the question is, how can we solve such problems? Right? So for this, let me define the problem formally, all right, for any functions. So again, this will be an infinite horizon problem. This is most of the time what we focus on. And there will be some reward function, okay? That reward function will depend on ut, xt, and sometimes it depends on t, all right? And there is this discounting term where rho is positive. So here the control variables are u, all right? Now this is subject to what? This is subject to typical non-negativity constraint, but here be careful because these are vectors, okay? So when I write that, I basically imagine these are my control variables and there are of them, okay? Then for each x, because x's are also vectors and the dimension is that, okay? Now for x's, I have the transition functions, okay? Fi, again, ut, xt, t, okay? So this is true for all, so this is true for all r, okay? And this is true for all I, okay? Then again, for each I, the initial value is given, okay? So let me check the notation in your text. UKR, okay. So This is not correct. UKT greater than or equal to 0. And this must be true for all K. Now K goes from 1 to R, and I goes from 1 to N. Okay? So what do I know? I know I have a set of control variables, UKTs, a set of state variables, XT. I know how for each for each state variable, my control and states let this evolution, okay, govern this evolution. I want them to be non-negative, and I know the initial values of my state variables. Okay. Now to solve this problem, we can use two things. First, we can use what we call present value Hamiltonian, or we can use current value Hamiltonian. Okay? They lead to the same result. Okay? They lead to the same solution, and eventually I would recommend you to use current value Hamiltonian, but I will show you both. Once again, in each of, so this is like your Lagrange, okay? So Hamiltonian is like Lagrangian, okay? They have the similar function. So we first define our Hamiltonian, then we're gonna write first the conditions by using the Hamiltonian function, okay? Now let's start with the present value Hamiltonian, okay? Present value Hamiltonian will be defined in this way. So first, you have the objective. And then you have the constraint. Then, for each variable you have, you're going to have this. Maybe I should write it in this way. You have, for each constraint, PIT times FI UTXTT. Okay? So here, PITs are non-negative, all right? And they are the shadow prices. Okay? Again, shadow prices are like Lagrange multipliers. Okay? Because they're non-negative and they still show me the cost of the, violating this constraint, basically, right? It's the cost of violating constraint. So we construct it in the same way, right? In the Lagrangian problem we studied earlier, remember we have f of x plus lambda j gjx. Remember this? So the same logic, but now, of course, it changes in time. It changes in time, right? Now, the first order conditions are like this. First, with respect to your control variables, you have this, right? This part is the same. Right? This part you remember well. Next, you may want to have the constraint itself, right? So for each I, you have xit equals fi ut xt t. Okay, so this must be true for all I. Then, for each p, you have this. Now, this is called co-state equation, and again, this must be true for all I. And I will explain each of them in a moment. Just don't worry. Finally, you have, so this is 1, this is 2, this is 3, and the 4 is this. You must have the transversality constraint. So here you have limit t goes to positive infinity, pit xit equals 0, and this must be true for all I. This is called transversality condition. Okay. Now I will explain each of these. All right, but let's start with the simplest one. Right. Now the simplest one tells you that this is 2. Right. The law of motion should be satisfied for each state variable. Right, because this is the law of motion. If I'm choosing this optimally, right? If I choose ut optimally, then the evolution of xt should follow this, because this is my constraint, right? Next, 1 is easy, right? Because I know the marginal benefit obtained from this should be either equal to 0 or less than equal to 0 if there's a corner solution, right? Remember these 3 figures. Optimality will be there, would be here, or would be there. Here, the derivative is less than 0. Here, derivative is 0. Here, derivative is 0. Okay? So 2 is done. 1 is done. Let's look at 4. Now, what does this tell you? Think about it. Translate this mathematical thing into English. It is a, go ahead. Yeah, go ahead.
If we value the xit, we must consume all of them when time goes to infinity, positive infinity, or we just don't consume them. Either time, there is 4 is equal to 0.
All right. Yeah, that's correct. So if value, the shadow price is positive when t goes to positive infinity, obviously I am valuing this resource, right? This resource creates a value for me because it increases my Hamiltonian. So Hamiltonian here is your maximum function, right? But if it is positive, right, this condition tells me that you should use all of it. You should exploit this resource, whatever it is, at the maximum. Because there is no tomorrow. There is no tomorrow after positive infinity. And if you are valuing this, if you did not make it value go to 0 in finite time, then this is a rationality constraint, basically. Okay, it forces you to consume all of this resource. If on the other hand, PIT converges to 0, then you realize one thing. Okay, wait. I do not care about this resource when time is sufficiently large. So that resource becomes valueless to me. It does not change my utility. It does not change my objective function. Then I don't care about this resource, right? I can consume all of it. I can consume none of it. Doesn't really change because its value converges to zero. All right? This means I obtained the entire utility I can obtain from it because there is a potential utility there, as in potential energy and kinetic energy, right? There is this potential out there, and in time I'm exploiting this potential for my own benefit. At some point, if it goes to zero, then I can consume the rest, I can waste it, I can throw it out, etc. All right? My typical example here is this. So suppose that this is a fossil fuel. All right, this resource is a fossil fuel. Now in the future, while we still have fossil fuel under the soil, we may have developed sufficiently productive electrical-based or hybrid technologies, okay, or some government would prohibit the use of fossil fuels, all right, then the value converges to zero. Okay, then we don't care about it. All right, that can still be there under the soil. So that's the notion. But if we are still valuing that resource, then we should consume all of it. In the cake eating example, if the cake is still good, if it is still delicious after 2 days, and I'm still valuing that cake, then I should consume it because it increases my utility. If there's positive value, then it should increase my utility. Okay. Now, what about this? The cost state equation. What does it tell you? Now, let me open a new page. Let me write the Hamiltonian once again. Hamiltonian is defined in this way. So there is this objective function, depend on my control state and in general time. There's the discounting term. Plus, I have the constraints, PIT, FI, UT, XTT, okay? And that condition tells me PIT dot equals minus the derivative of Hamiltonian with respect to that resource. Let me check one thing. Yes, okay. So, what does it mean?
Value change in time.
Oğuzhan, I cannot hear you well. Could you speak up loudly, please?
Okay, value change in time.
Yeah, that's the change in value in time for resource
Yeah.
I. Why it must be equal to this?
Sorry, I can't hear that.
So why that change in value for resource I should be equal to the minus and the derivative of Hamiltonian with respect to this resource?
If we consume more of the XIT, and then XIT will depreciation in as view.
Yes, so think about this derivative term, okay? Think about this derivative term. If this derivative truly reflects the resources contribution to my welfare, right? It is how it is defined, right? Because Hamiltonian is my welfare basically, right? Plus the, plus this constraint term. But if I realize this benefit, then its value should depreciate. Okay? Because this potential is now become realized. And the potential contribution becomes the past contribution in time, right? When time goes from t to t plus delta t, right? Where delta t itself is very small. Then I already realize what this profit is. If it is, for instance, a firm problem, right? In a firm problem, let's write the firm problem. So maximize. What was profit again? Profit was P times Fk, right? Minus IT. So this is from 0 to positive infinity. E to the minus RT, right? dt. And I had IT between I min, I max, okay? And then I have K dot T equals IT minus delta KT, right? And I have K0 positive. So the Hamiltonian is what? It is P FKT minus IT times e to the minus rho t, right? Plus PT, there's only one state variable, PT, IT, delta KT. So how do I write this constraint here? Well, the derivative of the Hamiltonian with respect to K, right? So I have e to, so this is RT, by the way, not rho t, this is RT. So e to the minus RT, P, F prime, KT, right? Then plus PT minus delta. Okay? Now this must be equal to minus PT dot. Right? This must be equal to that. Oh, wait. I have two P's here. So this is entirely confusing. Let's make this problem a real problem. Sorry about that. So let's make it a real problem. FKT. Let me also correct this. Okay. So I have F prime KT here and PT delta, and minus this should be equal to P dot T. Okay. So what do I learn from here? Let me do this. From the other first order condition, you need what? You need, with respect to IT, you have the derivative of the Lagrange with respect to IT equals 0. Let's suppose IT is between I min and I max. Okay? So what does it tell me? It tells me that I have minus RT right here, from here. I'm taking the derivative of the Hamiltonian with respect to investment. And then I have PT. This must be equal to 0, right? So I actually know PT is equal to e to the minus RT. So if I put this in here, what do I learn? I learn PT times F prime KT minus delta PT equals minus PT dot. So I can actually write this in this way. I can actually write this in this way. PT dot plus PT F prime KT equals delta PT, or PT dot divided by PT plus F prime KT equals delta. Okay? Now, what does it tell me? I'm accumulating this capital as a firm. Okay? I'm accumulating this capital as a firm, and I have a couple of benefits and a couple of costs, right? What is the cost term? It's the depreciation itself. This is the physical depreciation of capital, right? I'm paying for it. Then what is the benefit? Well, benefit is either today's benefit, because when I have KT today, it increases my productivity, right? This is the marginal productivity of capital. Okay? And also, I have the future expectation, right? In the future, there is this growth of value. Now, that growth of value plus today's benefit must be equals to today's cost. Or you can put it even in a different form. You can actually write this. So the increase in the value must be equal to minus net benefit. Okay? Because the net benefit, once it is realized, it is past. So I should optimally decrease my value. Okay, I decrease the value by the same percentage rate that is equal to the marginal benefit. So in this sense, this is actually a kind of asset pricing equation. Okay, or no arbitrage equation, because in some versions, these resources will be marketable. So you can buy and sell these resources, and optimality will require you to have no arbitrage opportunity. You know what arbitrage is, right? So you can sell, you can buy in the lower price and you can sell at a higher price. So this type of optimality constraint, the cost state equation, will tell you that you will not have any arbitrage equation. And this will be an asset pricing equation, because here, when we call pricing, of course, we mean the shadow price. So the asset here does not have to be sold in a market. You are accumulating this asset as a firm. Okay, or if you are a consumer, you are accumulating your wealth as a single consumer. You are not interacting with other agents. You are not selling your wealth. You are just hiring it in a savings account. All right, but sometimes you buy and sell these products. Okay, so then you can talk about prices. So that's it. Again, let me go back to this. Oops. So let me. Why is that huge now? Okay. So as you see, the change in the value of this state variable, okay, the change in the value of the state variable will be equal to the benefit of it for my welfare times minus 1. Okay, if this is now increased, I decrease the value I attach to it by the same percentage rate. Okay, that's notion. In that sense, there's a, so this one is an asset pricing equation. Okay, so these are the first of the conditions, and now I have less than 3 minutes. Let me stop here. So if you have questions, comments, I can answer them. In the next hour, we're going to continue with the second order conditions, and then we're going to have some examples. Anything? So if you think about it, the first of the conditions dictate us in some sort of rationality. Okay? If it is valuable, consume all of it. Change the value depending on the benefit, right? Benefit today. Then choose your control variables to maximize your Hamiltonian, right? Find the stationary point, either at an interior point or on the boundary. And that's it. And all these should satisfy the transition equations, the differential equations we have here. Okay. Time is almost 2:30. Let's meet at 2:45. Okay, again, after 15 minutes. Okay.